structure here, and let me just ignore the rod. Okay, the rod has also a certain amount of mass, but for now, let's ignore the rod. Suppose we have the rod on the coordinate system, and one has its x coordinate and y coordinate. Two also has its x coordinate and y coordinate. And we want to find the coordinate of the center mass. Then we use the mass of one times its coordinate. Its coordinate is 1. Say that's 1 meter. And the other one is 0.3 kilogram, and the coordinate is 5 meter. And then here we have the 0.1 plus the 0.3. So that's the total mass. Okay. We then have the 0.01 plus this 0.1, I mean 1.5. 1.1. Okay, sorry, 1.5. Okay, and that's meter times kilogram, and here we have 0.4 kilogram. And that will give us a coordinate, 1.6 over 0.4, so that's a 4 meter. So the center mass is going to be just a location, a coordinate. That's right here. This is then the center mass. So it's just a location. All right. Now, if you have also the y coordinate, then the y coordinate would also have the same form of equation. You have the total mass divided into m1, y1 plus m2, y2, and so on, and so forth. Okay. That way you have both the x, y coordinate of the center mass. All right. So, for example, if instead of having it along the x-axis, and you have it going like that. So that's a 0.1 kilogram, and this is a 0.3 kilogram, and this is a 4 meter. Then the coordinate would be still be here. This is the center mass. Okay. As you can see, this is a 3-to-1 ratio. Okay, 3-to-1 ratio. So that's a 3-to-1 ratio. Okay. If this is a straight line, of course, this has got the x1 and the y1, and that has the x2 and the y2. So the center mass will have the x and the y coordinate of the center mass. Okay, it's just 1 point. Okay. Therefore, you can do for both the x and y coordinate, and you find that it's going to turn out to be 3-to-1 ratio along the line joining M1 and M2. If the masses are 1-to-3 ratio, okay, masses are 1-to-3 ratio, then the center mass is closer to the massive object. And so, center of mass is an interesting concept. Now, we have a leaning power. Okay, that how many of you have been to pizza? Italy. Pizza, Italy. Not pizza to be eaten. Okay. Yeah, you should go there. Beautiful marble building. I think they allow people to go out. But anyway, the condition for this not to topple is that the center of gravity is within the base. So the base is here. If the center of gravity is within the base, then it's okay. But if you have more chunk of mass, so that the distribution is such that the center of mass is outside the base, then gravity is going to pull the thing down, okay, and it's going to topple. All right. So the condition for this thing to stand there is for the center of mass to be within the base. Now, that's done. We have another leaning tower. Okay. And this one, of course, if you add on it onto it, what would happen to it? Topple. So what did I do? You turn it so that the mass distribution is so that it topples. And you can see that this is not uniform. Yeah. So if you put the heavier side on this side, then it's going to topple. All right. Now, if you look at this toy, what can you say? What can you say about the mass distribution? What? Symmetrical? Okay. About? Okay. Yeah.
The center of mass is near its nose.
The center of mass is
Near the bird's nose.
yeah, near the nose. It's at the nose. Okay, very good. Okay, so I'm holding where the center of mass is, actually. So we know then the wings would have weight, would have been weighted down, actually. If you look inside, they put weights here at the wings. Okay, so say you have that. All right, now let me ask you, if I try to hold this here, will it hold? It will not, right? Can't do that. Need a belt. So who is willing to lend me a belt? Anybody? Okay. Belt. Now, so I'm gonna add weight to this, right? I'm gonna add weight to this. Without that belt, I was not able to hold it. But with the added weight, I'm now able to hold on to it. So what happened there? Shifted the center mass. Now the belt has weight on this side of my finger, all right? And the center mass now is below my finger, okay? So this is then stable. And you walk, you see people that carry a flexible rod that walk on high wire, right? You can see that they do the same thing there. That is, person is like this, and the rod may be along like that. You see that the center mass is going to be somewhere here, down below the person. So it's quite stable. Okay. If you have the center mass above the support, you have the center mass below the support, okay, it's just stable. If you have the center mass above the support, then you have to do something like that to get it balanced, right? Okay, and once it tips, it gets worse. This is an unstable equilibrium. Okay? So that's the center. Now, tell me, let me see, which end is higher? This gadget here, tell me which end is higher. This end is higher. All right. We all agree on it. Okay, so I'm gonna have the thing climb up the thing. Okay. So what happened there? How come it's going from the low end to the high end? Okay, it's going against gravity to the high end.
So the mass gets lower as it goes to the end.
Very good. So it actually is going lower, not going higher, because this is widening. Right? The center of this cone here is lower and lower when it moves to the right. Okay. So that's interesting. That it may be a puzzle for the first time that you see it. Something is climbing. It appears to be climbing, but actually it's going lower and lower. All right. Let's see. Think. There's one more. Okay, when you support the object at the center of mass, let's see, ideally, I actually have one other piece. I don't see it here. Not there. Okay, if it's at the center of mass, right at the center of mass, then this is happy any orientation you have. Okay, but right now there's some unbalance there. So anyway, if you support it elsewhere, you know that the center of mass is always, or center of gravity is always below the support. And if you get it to go above, it's going to come down. So the center of mass is, center of gravity is always down below the support. All right. That said, let's look at our equation here.
Got it just in time.
The denominator is the total mass. And if we multiply both sides by the total mass, it is something like that. So if you think about